Oh, sorry, thank you for starting it. I appreciate it. This is not my week at all, period, in the discussion. How many of you are having a good week? Okay. I'm having one of the worst weeks in the history of weeks. Huh?
I feel sorry that it's happening.
Okay, so if we consider the scattering of an electron and a positron, positron's just E+, then there are two diagrams that contribute, and I won't label everything. Yes, sorry, oh, there we go. Okay, so there's a positron. Okay, and then I can also do this one. No, sorry, I'm going to change that. It's going to be a positron and an electron for reasons that will be obvious in just a second. Now we have the electron and the positron. And then we'll relabel these. Okay, so let's just imagine we calculate the first one, we get a contribution M1, we calculate the second one, we get a contribution M2. The question I have for Joey is plus or minus?
I think it's minus.
Minus what?
Well, when we were talking about it in class last time, when we kind of flipped things around, it was basically just like an overall sign change. So it's still M1 plus M2 for the total M, but M1 is equal to negative M2. Or sorry, M2 is equal to negative M1.
No. So you're going back to the right idea. So one of the ideas that we did at our very last demonstration in class was we had a diagram that looked like this. And then we considered this diagram where we took this one and we jumped down. And this constituted swapping two outgoing electrons, for example. And then these two diagrams, you need a relative minus sign. The question is, what's going on here? Am I just taking the two outgoing electron, or the electron and the positron? Or no, yeah, that's a positron and that's an electron. Am I swapping them? No. Okay, so you should add them, right? No, you should subtract them. That's why I asked you this question. Remember the other rule, so the rule was you can swap ingoing or outgoing electrons or positrons, or you can swap an ingoing electron with an outgoing positron. And if we take this diagram and we do that, we can actually swap this incoming positron and this outgoing electron, and we can basically swap them. So we can say, all right, fine, I'm going to do this, and I'm going to do this. Okay? So this remains the same. This becomes an outgoing electron. This becomes an incoming positron. Okay? And then I'll label all the momentum the same. P4, P1, P2. And then you realize this diagram is exactly the same as this one. Because you just take these two vertices and scratch them out. Okay, so it's just an example of swapping an incoming positron with an outgoing electron and realizing that it takes this diagram and deforms it into this one. So those are the same, therefore you need a minus sign. Yes?
Incoming positron, outgoing electron.
If you switch them.
Swap where they are, like whether they're ingoing or outgoing.
Yes, they're swapping their role in terms of ingoing versus
And
outgoing.
if it produces the same thing you had before,
The same thing I have here.
then it's a minus.
Yes. But, I mean, this is just a detail, don't worry about it, it's not gonna play a huge role in what we're gonna do. Yeah?
Who was the thing you said? You could switch that between positron and outgoing electron. So what was the other one?
Or you can do an incoming electron and an outgoing positron. It's just if you do a particle versus an antiparticle pair to it, and incoming versus outgoing, swapping those, you get a minus. If you have both of them coming out and you swap them, they have to be the same. They either have to be both electrons or both positrons. Does that make sense? Okay. All right, so that's just a detail which I wanted to end last time with, but now we're gonna get into some nitty-gritty calculations. It's gonna get really ugly, but basically what I'm aiming at is an evaluation to actual, basically numerics of the m's, so that we can actually get some formulas. And we'll end today, hopefully, with some formulas that you've heard of, okay? So first and foremost, I want you to consider E plus mu goes to E plus mu, where the lowest level contribution basically looks like this. And I'm doing E plus mu goes to E plus mu for a couple of reasons. One, because mu has a much larger mass than E, so we're going to make an approximation at the end and derive a formula that you've hopefully seen before. And also, since it's E and mu, this is the only tree level diagram that contributes. We can't swap E and mu because they're different particles. You can swap these if they're both electrons coming out, but this is an electron and a mu and you can't swap them, okay? Let's label up our momenta, P1, P2, P4, P3. And the wonderful thing about this is the answer is exactly the same as the answer I derived when I did this with 2 electrons. Because the answer doesn't really care if, I mean, the only thing that's going to change is the mass of one of the electrons is going to become the mass of a muon. But I can just write down the m that we got last time in class. So this is going to give me m is u bar 3 I g e gamma mu u1 u bar 4 I g e gamma nu u2 times minus I eta mu nu over P4 minus P2 squared times I. Okay? So notice these are spinner sandwiches. This is an adjoint spinner, this is a spinner, so the combination of those is like taking a row vector and multiplying it by a column vector, just gives you a number. And then this is a spin matrix in between, but that matrix just gets absorbed. And similarly, we have another spinner sandwich here. So overall, this thing is largely scalar in spin space, okay? Now, in case you don't remember, these polarizations, okay, the polarizations of these things, of the U's and the U bars, those are something which we're actually going to, and I said this wrong, and Ross fortunately corrected me after class, we're going to average over the incoming polarizations and we're going to sum over the outgoing polarizations. Okay, so I said it last time, it's like we don't actually prepare the polarization of the incoming beam, so you want to average over polarizations of what's coming in. And then when you measure what's coming out, you don't measure the polarization, so you just want to sum over all the polarizations coming out. So this is actually going to be a very important step in this process, is handling these polarizations. So let's go ahead and get started. So if I am considering the polarization of the ith state, then I can imagine that I'm basically doing a linear combination of the 1 and 2 polarizations. Okay? Whoops. All right. Now, like I said, we're going to average over the incoming polarizations and we're going to sum over the outgoing, but of course averaging is started out by summing and then dividing by the number, so we're going to just first and foremost look at summing the polarizations and then we'll just throw in a factor to get an average later on. Now to do the average slash sum, first and foremost note that M contains generically terms of the following form, and I'm going to be sort of generic in my notation now because it'll simplify what I have to write down. But basically, it's going to be a bunch of terms times u bar A gamma 1 UB times some other stuff. Okay? So again, this is a spinner sandwich. Spelled wrong, as usual. This is a spin matrix. All right? And I'm going to give the matrix which is inside of here, it's just a gamma, but it, you know, in this case it might be IgE gamma mu. Remember, gamma mu is a spin matrix. I'm just going to give it its own label 1, and then other terms, this is just one term in M. So if, for example, in this one there's 2 of these. But anyway, I'm going to give the gamma just a label 1 and then gamma 2 because they're going to carry different, even if they're the same matrix in spin space, they're going to carry different space-time indices, like one carries mu, one carries mu. So I'm just going to give them separate labels. Okay, but this is my generic labeling, and this is what I'm going to work with, and then we'll go back to the notation in due time. Now, to use M, obviously, in Fermi's golden rule, we have to take the complex square of it. And so this is going to take this, and it's going to render us with u bar A gamma 1 UB times the quantity u bar A gamma 2 times UB star. Okay? So obviously, I'm going to get a bunch of factors in here, but I can always, since these are spinner sandwiches, I can move them right next to each other because they're basically scalars in spin space. Even though this term is the same as this term, I'm giving this a different label, okay, for the same reasons as I argued up there, okay? Now, this is a number in spin space. So I'm complex conjugating it, but it's a number, so I could also transpose it, right? But if I also transpose it, then that's basically taking this and turning it into a dagger. Okay. It's a number, so transposing a number doesn't change anything. So this dagger is just complex conjugation times transposing, where the transposing doesn't really do anything. However, if we want to take this operation and apply it to all of these, transposition does a special thing because this becomes UA gamma 1 UB, and then I reverse the order to get individuals. Okay? I think I could do better than that. Yeah, let's do better than that. Okay, so this thing I can say is U dagger B, gamma dagger 2, and then I can just use the definition of U bar in terms of U. So this, as it turns out, is U of A dagger gamma 0 dagger. Okay. Remember, U bar of A is UA dagger gamma 0. Okay, so I'm just plugging that in here, and then I'm daggering the whole thing. Okay. Oh wait, I'm daggering this, so I can actually reverse the order of these, and then I'm going to get U dagger B gamma 2 dagger, and I'm just going to scoot this over here for a bit. Gamma 0 dagger UA. Okay. Oh wait, gamma 0 dagger is the same as gamma 0, so I actually don't need that. Moreover, gamma 0 is equal to what? Anybody remember? Say it again?
Yeah.
The identity. So I can actually sneak a gamma 0 in here. Okay? oh wait, hold on, this is just U bar of B. I can call this thing gamma 2 bar, okay? And then this, of course, is UA. So at the end of the day, my contribution to m squared is U bar A, I'm just copying what I started with up here, gamma 1 UB times U bar B, gamma 2 bar UA. Okay. Looks pretty good, right? What are we about to do? Any takers? I'll just flip through cards till somebody has an idea. Tanner.
I do not know.
Tanner. Jared. Any idea? What are we going to do with this m squared expression?
Substitute for U.
Well, no, we're gonna sum over the polarizations. Okay? Now, if I'm gonna sum over the polarizations of all the spinors in here, notice first and foremost, I might start by summing over the spins associated with particle B. All right? Oh, hang on. If I want to sum over the spin states associated with the factors US and U bar S, these are the same particles, so the spinors just take this form. I mean, I don't have to label them here. But I'm going to sum over these polarization states, or these spin states. This is going to give me gamma mu, P mu, plus MC, which we often call P slash plus MC. Okay, you proved that in your homework, or you showed some examples of that in your homework. This is where we're going to use those results, okay? So what I can do is I can now say, all right, let me come up here. If I sum over the spins associated with B of the expression m squared, then I'm going to get U bar A, gamma 1, times P slash of particle B plus the mass of particle B times C, times gamma bar 2, times U of A. Okay? All I did was I took this combination UB, U bar B, and I used this summation to replace it with P slash plus MC. Okay? Now, am I going to be able to do the same for UA? Well, I mean, remember, this has got a gamma mu in it, which is a spin matrix. And this is a spinner, and this is a spinner. I can't just arbitrarily move things around. However, turns out if we do a little trickery, we might notice this is a row vector, this is a column vector, and this is a matrix in spin space. Okay? The gammas have matrices in them, and the P slash has a matrix in it because P slash has gamma mu. Okay, so, but all together inside is a matrix. Now for something which you might or might not be familiar with. This is a row times a matrix times a column, which of course gives you a number. Right? Everybody on board with that? You know, it's this times that. It's row times matrix times column. Okay? However, how many of you knew this? This can also be evaluated by taking the trace of the matrix times the column times the row. Yeah, I knew that. Now I was waiting for you to write it. Okay. Turns out that's true. Okay? Which means, of course, that we can now say that the sum over SB m squared involves the trace of gamma 1 P slash B plus MC gamma bar 2 times UA U bar A. Okay? Again, this is just the matrix times the column times the row, the column times the row, UA U bar A. Now we're in a position to sum over the spin states for particle A. Okay? So in the end of the day, we can say if we sum over SA and SB for n squared, then we get dot 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 trace gamma 1 PB plus MBC, and that should really put the mass label there, times gamma bar 2 PA plus MAC. Okay? Again, this is one of those tricks that you will use in evaluating calculations. Figuring this shit out, forget it. Don't worry about it. Well, you'll just see the derivation, you go, and then you'll take the result and you'll apply it in doing finite diagram calculations, okay? So don't worry about that. In fact, I might give you a couple of homework problems to kind of, grind through some of this, but don't worry about this. This isn't the important part of the story, okay? I'm about to give you the tool. But if at some point we summed over VV bar as opposed to UU bar, then in that case we just replace it with P minus MC. So if you're using antiparticles and you're summing over the polarization states associated with VV bar, then you're going to replace it with P slash minus MC versus P plus. Okay? So here is the rule as we can summarize it now. I'm going to do it here. I'll probably regret this, but whatever. It's always fun. To impose the sum over SA and SB, replace U bar A gamma 1 UB, U bar A gamma 2 UB starred with trace gamma 1 P slash B plus MBC gamma bar 2 P slash A plus MAC. Okay? That's so good, I'll put a little box around it. Because if you think about it, when we go to square this, we're going to get this thing times itself conjugated. We're going to get this thing times itself conjugated, but we just apply this rule to both of them. All right? So I'm going to put this to work, but I'm actually going to put it to work in a slightly different example just so I have some V's in it. So imagine I take this diagram and I replace the mu with mu plus. So I'm just basically going to reverse the direction of these arrows. It's not going to change much, okay? But if I did that, then M comes out to minus GE squared over P4 minus P2 squared, V bar 1, gamma mu, V3, U bar 4, gamma nu, U2, eta U nu. Okay? All right. So I'm basically taking this expression and I'm replacing the 1 and the 3 U's by V's. Sorry, antiparticles. Okay. All right. Now let's consider m squared. And this is going to be GE to the 4th over P4 minus P2 4th, and then we're gonna get V bar 1, gamma mu, V3, and just bear with me, this is gonna suck. If anybody's got any jokes, go ahead and tell them. Or not. What do you call a what? Oh man, that's a hilarious joke. You're making me laugh my ass off right now. Oh, shit.
Definition of a Freudian slip, when you say one thing and mean your mother.
You should tell the sausage joke.
I told the sausage joke before, I won't tell it again. It's such a funny joke though. Okay, there you go. I multiplied it 8. All right? Now we can grab these right here and these right here, and they will reduce to trace gamma mu p slash 3 minus m3c gamma bar lambda p1 slash minus m1c. Okay, again, there's minuses in there because these are antiparticles. They're v's instead of u's. All right? But I'm basically just applying this rule. It's just they're antiparticles, so I put minuses in there. But that's what those will give me, and then these will give me trace gamma nu p slash 2 plus m2c gamma bar lambda alpha p4 slash plus m4c. Okay. So now if we want to average over these, and I should say that this is, and I don't know what notation I was using before. Yeah, I guess I should put in 2 summations here. But at any rate, this is just going to be understood that the m squared we're using has the sum of those. And now if I'm going to average it, I just throw in a factor of 1/4. Okay, because I have 2 particles coming in and they each have 2 polarization states, so I get a factor of 1/4 for the averaging of the income. All right. And then, well, this just times this. And then I have an eta mu nu and an eta lambda alpha. So that is my expression for m squared as I would use it to calculate something. All right. Now, and this is a trace, make sure you realize that. Now, here's the thing, m, it should be a scalar, right? But this thing has gamma mu, it's got a gamma mu there, it's got a gamma, it's got a gamma there, it's got a lot of spin matrices in it. So how are we gonna go from these being spin matrices to this being a scalar? Let's ask Sean. How are we going to go from these being spin matrices to this being a scalar? It's not how are we going to go, it's what did we do in this expression?
We multiply them together. Oh, we add them together because we take the trace.
Take the trace. This trace is a trace over matrices in spin space. That's what the trace is with respect to. Okay. So yeah, if you have a spin matrix and you trace it, you get a scalar. Okay. So so yeah, all we have to do is take the trace of these, and we're done. It's pretty awesome, right? Yeah.
Where did those metrics come from?
These?
Yeah.
They're just taking care of the fact that this is gamma nu, gamma alpha, and those have to be combined. They were born and raised here, here, and then when I squared it, I had to relabel the lambda alpha and the lambda, because I don't want to use mu nu in this term and this term, because that would imply that you're summing over everything simultaneously. Okay, that's why I gave these labels gamma 1, gamma 2, because even though this looks exactly like this, the gamma matrices have to have different labels. You follow?
Maybe
So, and these are trivial in spin space, so I just yanked them out. They're just metrics.
Okay.
They're scalars
right.
in spin space.
So there's,
Yeah, I could yank them out. Okay, any other questions about this? All right, let's dive in. We've got to evaluate these traces. And the news is good, because it turns out that you know exactly how to evaluate these. Isn't that awesome? You guys know how to do it? Let me remind you. First of all, let me remind you, so first of all, notice, the only thing in this expression, which is non-trivial in spin space, is the matrices, and they're all gamma matrices. This is a gamma matrix. P slash is gamma d mu. That's a gamma matrix. That's a gamma. All of these are gamma matrices. Okay. Well, look at this. Maybe you will, and maybe you won't remember. But if I have the trace of a product of 4 gamma matrices, this is equal to 4 times a bunch of metrics, or inverse metrics. Does that look familiar? Yeah, hell yeah. In fact, it gets even better because the trace of any 3 is 0, and the trace of 2 is 4 times the metric, or the inverse metric. Okay? These are all things that you played with in your homework. Now we're going to use them. Okay? So let me start with the trace of gamma mu p slash a plus or minus ma c gamma bar lambda p slash bar plus or minus mbc, and I'm going to call this x plus minus. Okay? That's actually a p slash. Okay, now first and foremost, this thing right here, remember the definition of the bar of something is basically that you surround it by gamma zeros. Okay? Actually, you surround it by, you dagger it, and then you surround it by zeros. Okay? This is non-trivial, but it is true. This is basically just gamma lambda. Okay? True, but non-trivial. So don't worry about that. I mean, you could prove it. You just pick a gamma lambda matrix, and then you hit it, you transpose it, you complex conjugate it, and you surround it by gamma zeros, and you'll get back the gamma matrix you started with. Okay? All right. Now, well, okay, first and foremost, remember, if you have the trace of the sum of 2 matrices, this is just the sum of the traces of the individual matrices. This is going to be useful because when we multiply this out, we're just going to get the trace of a sum of terms. And this is just saying if you got a trace of a sum, it's a sum of traces. Okay? So here we go. This quantity x plus and minus, if I just multiply this thing out and I break it up into a bunch of traces, I'm going to have trace gamma mu p slash a gamma lambda p slash b plus minus trace gamma mu p slash a gamma lambda mbc plus minus trace gamma mu mac gamma lambda p slash b plus trace gamma mu mac gamma lambda mbc. Okay? Now, remember, it's kind of boring, isn't it? use this, and we can also use that if I have a matrix which is multiplied by a number, and this is what I'm tracing over, but if I multiply the matrix by a number, then that just pops right out, okay? So this is same as alpha times the trace of M. Okay? Now why would I say that? Well, look at this. This involves a gamma. This is gamma times P, P mu. This is a gamma. This is a gamma times P mu. The P mu's, remember, P slash is gamma mu, P mu. So if I expand all of these slashes, all of these slash P's in terms of gamma P, I can pull the P's out because the momenta are trivial in spin space. Okay. So just as an explicit example, in this first one, I can say, all right, that's P mu A, P nu B, and I probably should put, I can do nu and alpha. And then this is going to be trace gamma mu, gamma alpha, gamma lambda, gamma nu. Okay? Everybody follow that? I'm just taking the P's, I'm breaking them up into gamma times P. The gamma is non-trivial in spin space, so it has to stay in the trace, but the P I can pull out, okay? And I'm just labeling it, this is the space-time index, and this is just the A and B for labeling which particle it's associated with. But look at this. Boom. Yes?
You say trivial, do you mean it's a scalar?
Yeah,
Okay.
yeah, it's trivial in spin space, so it's a scalar in spin space. Okay, so clearly on this term, I can use the first formula. What about this term? What can I use?
B.
Which one?
B. Formula B.
Formula B, because this has got 1, 2, 3 gammas in it. Everything else will come out. What about this one?
Also that.
Also that one. What about this one?
Also C.
I use C because this has got 2 gamma matrices in it. Okay? That cool? Everybody got that? All right, so this is going to 0. This is going to 0. Okay? Which, first and foremost, tells you that x plus is equal to x minus. Because the only thing that distinguished plus and minus were these terms, but they're 0. Okay? So now we can finish up with what we have left, and yeah. So if I apply this to this expression, and I apply this to this expression here, then what I'm going to end up with, and I'll just call it x now, is 4 times PA mu PB lambda minus eta mu lambda PA dot PB plus PA lambda P mu B plus 4MA MB C squared eta E lambda. Okay? Okay, so did everybody understand this term? I'm basically taking these 2 vectors and I'm contracting them with these combinations of the metric. So just to give you an example, the first term is going to take the alpha index and raise it to become a mu index. Boom. The second one is going to take the, and I use lambda instead of, yeah, that's my problem. Mu, alpha, lambda, beta instead of nu. Shoot. Okay, I could just rewrite this with nu instead of beta. There we go. Now, this this is going to grab the new index and raise it to a lambda index. So you get two p's. This one is going to take mu and raise it to lambda. Well, that's just going to be that. That is that factor. But the second one is going to take the alpha and the beta, and it's going to raise one to be the other, so you're going to have the inner product. Okay? Do you need more detail, or does that kind of make sense? If you wrote it down, it'll make sense. I'm just going to skip that. And then this, of course, just follows from that second term. All right, so now we can write our final expression for m squared, and I think I'm going to do it over here, because we're going to use this in a few minutes. But our final version of m squared is the following. One over 4 GE to the fourth over P4 minus P2 quantity squared, or it's quantity to the fourth, times, now, you just have to remember that we're going to have that times itself. So this is going to give me 16 times P3 mu P1 lambda. Now it's time to tell a joke, if anybody's got one. Ross, why don't you tell the sausage joke?
I can't do it.
Yes, you can. I've got faith in you. Okay, fine, you don't have to.
Sorry.
Times, no. You guys really need to bring your joke books to class. Okay. Nice and ugly. I know. All right. But I can now employ these things to basically take stuff and make it into dot products between vectors. So in the end of the day, this is going to become 8 GE to the fourth over P4 minus P2, quantity to the fourth, times, and now I can write this as P3 dot P2, and notice I'm putting a dot product, but that's really, when I write dot, what I mean is this. Okay, it's the inner product on the force base, so you use the metric to do that, but I'm just going to write dot for simplicity. P1 dot P4 plus P3, whoops, the 3 on the P. P3 dot P4 P2 dot P1 minus P3 dot P1 ME squared C squared minus P2 dot P4 M mu squared C squared plus 2 ME squared M mu squared C to the fourth. And now I just want you to notice the magic. This quantity is now written only in terms of the dot products of space-time vectors. There's no more spin story to it. All our spin matrices are gone. Okay. Now this, of course, will sit nicely inside of the scattering theorem. So let's actually put this to use in an example, an explicit example. And then we'll take a special limit and show you some formulas that you've possibly seen before. Okay, so this is two-body scattering, and remember, for two-body scattering, Fermi's golden rule says that d sigma d omega is basically h bar c over 8 pi quantity squared times the degeneracy factor times the square of m over E1 plus E2, quantity squared times P final over P initial. Okay? And this is in the center momentum frame. All right? Now, we have our factor. So this is for independent polarization states, but of course we're going to average over the incoming and so some of the outgoing. So instead of m squared, we're going to do the average of m squared, but that's fine. Now we've got an approximation we can make. First and foremost, m mu is much larger than the electron mass. The mass of a muon is much larger than the electron mass. Okay? This is going to let us make some rather radical simplifications. So first of all, it means that E2, the energy of this is just the energy of the electron, okay? But moreover, this is way, way less than the mass of the mu times c squared. So we're going to, I should say, this does not apply. So we're going to take this and assume this, okay? So what I'm saying is, first of all, I know that the mass of the muon is way the hell bigger than the mass of the electron. Furthermore, I'm going to assume that the energy of the incoming electron is quite small compared to the rest mass energy of the muon. Okay? That's not hard to do. The rest mass of the muon is just huge compared to the electron. Okay? But it's an approximation.
Is that like the total relativistic energy
Yep.
of the electron?
Yep. Okay? So now we get some nice results from this. First of all, we find that basically let me say this. The final outgoing momentum has the same magnitude as the initial ingoing momentum. Because if we're in the, so here's the important observation. If mu has a hell of a lot bigger mass than E, and the energy that I'm giving E is itself super tiny compared to the mass, the rest energy of this, what do you think is going on in the center of momentum frame? Okay, let me give you an example. So if I have a satellite, and I want to talk about their scattering, what is the center momentum frame?
Just the center point?
Yeah, it's sort of this central point, and the net momentum has to be zero, whatever. Now, let me take a satellite and the Earth. What do you think the center momentum frame is? Center of the Earth. Yeah. The Earth is not going to move. Okay? So in this story, we can basically assume that not only is the muon not moving, but it's not moving in the center of momentum frame. Only the electron is moving. Okay? Moreover, due to momentum conservation, the non-zero spatial momentum is going to be that of the electron and none for the muon because the muon's sitting at rest. So the electron's going to come in with some momentum and it's going to leave with the same momentum, except it could change direction. Okay? All right. Furthermore, we can say that E1 plus E2, well, I can just approximate the overall energy of the muon, since it's at rest, by the rest energy. Okay? But this is approximately m mu c squared. Because again, the energy of the incoming electron is very small compared to the rest energy of the muon. Okay? All right, so now we can say that the average d sigma d omega is going to be h bar over 8 pi m mu c squared times the average of m squared we can actually assign values for the vector momenta. So I'm gonna have the electron coming in with some momenta P2 and energy E. Actually, let me do this. Let me just say energy E and spatial momentum P2. And I'm gonna have, and this is of course the electron. Then I'm the muon sitting on its butt. I don't know why I've labeled this way. This is really weird. Anyway, okay. So after we have the muon sitting at rest, and then we have the electron shoot out at some angle, okay, with again energy E, because the energy is not changing, but the directionality of the P could change, okay? So now with this picture in mind, let me actually write down what the four momenta are for each particle. So P1, which is the muon, well, it's at rest. So it's, the time component is just m mu c, and the spatial component is 0. For P2, which is the incoming electron, well, it's got energy E over c, or the time-like component of the four momentum is E over c, and its spatial momentum is P2 vector. P3, well, once again, this is the muon, so it's just m mu c, 0 vector. And then P4 is going to be E over c, P4 vector. Okay? Now, in order, so do these make sense to everybody? Okay, and remember, P2 magnitude is the same as P4 magnitude. Yeah?
On the diagram, is that M sub u? Or is that?
This is M sub mu, this is M sub mu. It's the mass, it's the muon. You can just call it the muon. Just call it the muon. And this is the electron scattering away. Okay? So now that we have those four vectors in hand, we plug them in here. Okay? That make sense? All right, now remember, we used an approximation to get these forms of the four vectors. We could have been more general, but this is heavily approximated. Now we're just going to shove it in here. And when we do so, we will find the following. And I'm just going to skip straight to the answer, and you can look up the details in my notes. Okay, here we go. We're going to end up with d sigma over d omega averaged being, it's nothing too tricky in there, GE squared h bar over 8 pi p squared, okay, where p is just the magnitude of this. Sine squared theta over 2, all squared, times the mass of the electron times c squared, plus the momentum of the electron, of course, cosine squared theta over 2. Okay. Anybody ever seen that? No. Yeah.
Is there a vector multiplying and then you add a scalar to it?
Oh, sorry, that should be squared. Should be squared, sorry. Which, I mean, I could call that p squared, p squared, p vector squared, doesn't matter. Okay. So that's the same p squared you see down here. No one's ever seen this? It's called the Mott formula. Okay. This is the relativistic scattering cross-section, or the differential cross-section, okay, of a very light particle scattering off of a very heavy particle, where the incoming particle doesn't have that much energy compared to the rest mass energy of the particle it's scattering off of. Okay? If I were trying to apply this to the scattering of two electrons, forget it, because they have similar masses. Or if I wanted to send in the electron with a hell of a lot of energy, so close to or greater than the rest mass energy of the muon, forget it. None of that approximation will work in that case. All right? Now, there's one more limit we can take, which is going to make this even simpler, and that is we can take the magnitude of the momentum to be much smaller than the rest energy of the electron. Okay? This is essentially saying that the electron is moving hella slow. That is, this is the non-relativistic limit. The thing is you could have a relativistic electron and still have its energy be much smaller than the rest energy of the muon. Okay, even though it's relativistic, it's just the electron's so damn light. Okay, but if we take a non-relativistic limit for the electron, this simplifies even further, and it becomes d sigma d omega averaged is e squared. I'll write it the way I usually write it. G e squared h bar c m of the electron over 8 pi m e squared. Yeah, I can clean it up. I don't want v squared sine squared theta over 2. And then cleaning this up and replacing it with some other expressions, it's going to be e squared, which is the electron charge, divided by 8 mc v squared sine squared theta over 2. Has anybody ever seen that one? Yes or no? You think so?
Is that an ionic?
Yeah, this is the Rutherford formula. It's just the non-relativistic limit of the Mott formula. Okay? All right, so it's time for us to depart. You know, I'll give you some homework problems so that you can hammer on this, but I don't want you to get too lost in the details of this. Next time we come in, we will start looking at QCD. Okay, so we'll start taking this story to the QCD version. We'll probably spend a couple lectures on that, and then we'll take it to the weak interactions, and that's going to be a real shit show, okay? Because the mediators are massive, and you got all this crazy chirality of the spinners and the symmetry and everything, okay? But I just want to kind of dip your noses into these calculations for all three of the standard model forces. They're going to look different. You know, QCD's got 3 colors, 8 gluons. It's way more headachy. But anyway, so we'll look at applying this to that. The end of that story, though, and that's basically the content of this course, but the end of that story will actually lead us to a rather interesting observation. And that is basically the observation that all of these things which we've assumed are constants, like the electron charge, the electron mass, all of those things which we assumed are constants, are actually not. And this will broach the very, very interesting story of renormalization, which is going to open the doorway to incompleteness of the standard model and accept uninvited guests like string theory. But that's how we'll end the semester. Okay. So just a note, I'm going to add this into the notes, but I won't go over it today. There's a couple of cases where our Feynman rules haven't covered. So for example, if I have a diagram like this, and there's an internal loop, remember the Feynman diagrams say you start on an outgoing particle, and you go to the vertex, and you come here, da-da. Well, what about this loop in here? And the loop in here gets a contribution, which I've got the rule written down here, okay? And then there's something called the Furry's theorem, which is really cute. But anyway, that's an application to diagrams with interior triangles of fermionic matter, but don't worry so much about it. I'll see you all Tuesday of next week.